Hi dear students, today we will discuss about the topic real gas. But before going through the real gas, let's understand what is ideal gas. Ideal gas is a gas which obeys two things. First one is the general gas equation, that is known as PV is equal to nRT. First one is general gas equation, that is PV is equal to nRT, and the second one is all the postulates of kinetic theory of gases. Postulates of kinetic theory of gases. But among all the postulates of kinetic theory of gases, two postulates are very much important. Where first one says, two postulates are very much important. Where first one says the volume of a gas molecule is considered to be negligible as compared to the volume of the container. The volume of a gas molecule is negligible. And the second postulate is intermolecular force of attraction between two gas molecules is also negligible. Intermolecular force of attraction between two molecules is negligible. Okay, so to be an ideal gas, a gas must obey these two laws. But dear students, the thing is that no gas is ideal in nature. Rather, what happens is that some gas behaves, they show like ideal behavior under certain condition. What I told? Under certain condition, some gas shows ideal behavior. Okay, under certain condition. Then what are the conditions? The condition is, the first one is at low pressure, and the second one is at high temperature. So what happens under these two conditions that a gas behaves like an ideal gas? What happens at low pressure? At low pressure, okay, suppose when pressure is low, the volume is high. Okay, so when volume is high, a gas molecule present inside the container can be negligible as compared to the volume of the container, since volume of the container is high. And we studied here that volume of a gas molecule is negligible is the condition of ideal gas. So at low pressure, when volume is high, the volume of a gas molecule is negligible. So under this condition, a gas behaves like ideal gas. And what about high temperature? What happens at high temperature? Kinetic energy of gaseous molecules also increase. When temperature increases, kinetic energy of gas molecules also increases. Then what happens? The movement of the gaseous molecules becomes so fast, and when the movement becomes so fast, the attraction force between two molecules is less because they are moving in high speed. So the attraction between them is negligible, and that is our condition for ideal gas, that the intermolecular force of attraction between two molecules is negligible. And when kinetic energy high and they move very fast, intermolecular force of attraction between those two molecules get high. So at high temperature, again a gas behaves like an ideal gas. So under these two conditions, the gas behaves like ideal gas. Okay, so now thing is that what about other conditions? What happens at high pressure and low temperature? What about this condition? Dear students, what happens is that under such conditions, a gas deviates from ideal gas behavior. That means it doesn't obey the ideal gas laws. Okay, under certain condition, under this condition, the gas doesn't obey ideal gas laws. And Vanderwall was the person who introduced those kind of gases named as real gas. What? Real gas. So this is our topic of discussion. The gas that doesn't obey the ideal gas laws are known as real gas. And according to him, means according to Vanderwall, real gas have again two properties. So what is the properties of real gas? Real gas properties. Okay students, this is the properties of ideal gas, where it is said that volume of a gas molecule is negligible. So obviously the condition for a real gas should be it possesses specific volume. Means the real gas molecules possess some specific volume. And what about the second? In ideal gas, we told that intermolecular force of attraction between two molecules is negligible. So obviously, in case of real gas, the intermolecular force of attraction should not be neglected. I mean, the intermolecular force of attraction exists. Okay, so these are the two conditions for real gas. So according to this real gas, again what happens? Vanderwall proposed two correction. Those are named as pressure correction and volume correction, which is different from ideal gas. Okay. So now we will discuss about those correction terms. So as I told, Vanderwall proposed two corrections. But first one is volume correction and the second one is pressure correction. Okay students, so now let's start first volume correction. Volume correction. Before starting the volume correction, let's write the ideal gas law first. And what our ideal gas law says? Ideal gas law. And the ideal gas law is PV equals to nRT. And since we are using the ideal situation, we can write here PI VI equals to nRT. So what are these terms? PI is pressure exerted by gas molecules inside a container, where VI is the ideal volume. Listen, this is the most important term, where VI is known as ideal volume. That is the volume available for free movement of the gas molecules. VI equals to ideal volume. Okay, that is volume available for free movement of gas. And you know, N is moles of gas, R is gas constant, and T is temperature. Okay, so this is all about ideal gas law. Now suppose what to do? Suppose we take an ideal gas in a container of volume V. Suppose we are taking an ideal gas in a container of volume V. Suppose these are the ideal gas. So what happens here? Here Vi equals to V, where Vi is ideal volume. And what I told, ideal volume is the volume available for free movement of gases. Okay, and V is the volume of container. Volume of container. So you see here, this is the ideal gas. Okay, this is the ideal gas, and the ideal volume or the volume available for free movement of gases is the whole container. Means the whole volume of the container is available for free movement of gases. That's why the ideal volume is set as V. Okay. Suppose now we take a real gas in a container of volume V. We are taking a real gas in a container of volume V. As you know, real gas possesses some specific volume. These molecules are bigger. I mean, we can think like that. So these are the real gas molecules. And in this case, V equals to VR. Okay, V equals to VR, where VR is real gas volume. What do you mean by this? It means that since this container contains real gas, the real gas volume would be equal to the volume of the container. Did you get me? Since this container contains the real gas, obviously the real gas volume will be the volume of the container. So right here V equals to VR. Okay, so for ideal gas Vi equals to V, and for real gas V equals to VR. Then what we found here? Here Vi is not equals to V. Why? Why Vi or the ideal volume is not V? Because the answer is these real gases possess some volume. Okay, this real gas possess some volume. So what about Vi? Let's see what is Vi then. That means Vi, that is the ideal volume, it will be small than the volume of the container. Okay, because since ideal gas possesses since real gas possesses some volume, for real gas now Vi will be less than V. We can also prove it. See this. Okay, suppose this was a container of volume V, and now what we will do is that let's bring all these molecules, all these real gas molecules to the corner of the container. So if we bring all these molecules to the corner of the container, it will be something like this. This is the volume. Okay, so you see here, in this case the volume available for free movement of gas, the volume available for free movement of gas molecules is not V, rather it's less than V. And what is the volume available for free movement of gas? That is called Vi, or ideal volume. So in case of a real gas, the volume available for free movement of gases, that is ideal volume or Vi, is less than the volume of the container, that is V. Okay, so in this case Vi is less than V. So what we now need to do is that here also you can write, since V equals to VR in case of real gas, we can write Vi is less than VR. So what we found is that ideal volume is less than real volume. Okay, then ideal volume is less than real volume. So to get ideal volume, what happens? We need to subtract some volume from the real volume because real volume is the bigger term here. So Vi will be VR minus some V dash. Okay, Vi will be Vr minus V dash. Since Vr is high volume, so to get ideal volume, we need to subtract some volume from real volume. And this V dash is called volume correction term. So now let's derive this volume correction term. I mean, what is this V dash? Okay. So this was the ideal gas. Now first write this thing over here. Vi is equals to Vr minus V dash. Okay. If we name this equation as equation 1, where V dash is volume correction term. Volume correction term. So now let's find what is volume correction term. What is volume correction term? Okay, let's take two gas molecules of radius capital R, which are attached to each other. So this is one gas molecule. This is another gas molecule. Here radius is capital R, and here also radius is R. And if we draw circle around it, it will be like this. Okay, so this is gas molecule A and this is gas molecule B. So dear students, here you can see that the center of mass of gas molecule B can move freely everywhere except this portion. Okay, this center of the gas molecule B can move everywhere except this shaded portion or shaded volume, which is known as excluded. I mean, this is the excluded volume or free movement of gas molecule B. Okay, so for this two gas system, what will be the excluded volume? And this excluded volume for two molecule system, the excluded volume will be, listen, this is again if it will be a sphere, its radius will be now 2r. Okay, so the volume will be 4/3 pi into 2r whole cube. Okay, that is equals to 4/3 pi 8 r cube. So for two molecule system, the excluded volume is 4/3 pi 8 r cube. So what about one molecule? For one molecule, excluded volume is equal to half of this. Okay, half of 4/3 pi 8 r cube. Okay, so we divide this. It's 4. Okay, so it will be like 4 into 4/3 pi r cube. Okay, I rearranged it, and what I found is that for one molecule, the excluded volume is 4 times the volume of a gas molecule. Okay, so for one molecule, the excluded volume is 4 times the volume of a gas molecules of radius capital R. Okay, then for 1 mole of gas, excluded volume is equal to 4 into Na. 1 mole contains 6.023 into 10 to the 23 number of molecules, that is known as Na, into 4 into Na into 4/3 pi r cube. Okay, for 1 mole of gas, the excluded volume is this. If we replace this with B, suppose we replace this with the term B, then what happens? For n mole of gas, the extruded volume is equal to NB. For n moles of gas, the extruded volume is NB. And see here, this was the Vanderwall volume correction equation, where Vi equals to Vr minus V dash, and this V dash is the extruded volume. Because we want to subtract this volume from real gas volume, so this is the extruded volume. Now we can put this extruded volume over here, that is NB. So what we will get is that the Vanderwall volume correction equation will be now Vi equals to Vr minus NB. Okay, then what is B? This B is called Vanderwall constant, and it is also a size factor. Okay, this is also a size factor. So dear students, here we derived the Vanderwall volume correction equation, or we found the volume correction for Vanderwall real gas theory. So now rub this and write this over there. We finished it here. Now let this over there. Volume. The first volume correction we found it, okay? Volume correction equation, that is Vi is equal to Vr minus NB. Vr minus NB, where Vi is the ideal gas volume, Vr is the real gas volume, N is number of moles, and V is Vanderwall constant. Now let's see the pressure correction. Let's see the pressure correction that we made for real gas. Okay, so first see, in an ideal gas, the intermolecular force of attraction between two molecules is 0. Okay, so in case of ideal gas, suppose this is ideal gas, then the intermolecular force of attraction between the gas molecules is 0. That is according to gas law. That is means according to ideal gas law. And suppose the pressure exerted here is P ideal. Okay. Now what happens in case of real gas? The intermolecular force of attraction is not 0. Okay, in a real gas, the intermolecular force of attraction is not 0. Suppose we will take some real gas over here. Okay. These are the real gas. And suppose the pressure due to that real gas is P real. The pressure due to that is P real. This is the real gas. Okay. So here you can see some molecules are present at the center of the container, where some are going to strike the wall of the container. So what happens, guys? Since intermolecular force of attraction in real gas is not negligible, it means that if a gas molecule is present at the center of the container, it will be attracted in all directions. It will be attracted in all directions by other gas molecules. So here the net force is 0. Since the gas molecule is attracted in all directions, the net force is obviously 0. What happens here? Net force is equal to 0. But what about those gas molecules which are going to strike with the wall of the container. Like this molecule is going to strike with the wall of the container. So it will not get any kind of inward force from this side. It will get only inward force from these sides. Okay? From this side. So see here. Now it is getting an attraction force, that is net force is not getting 0, and since it is getting an attraction force, it means that now this molecule, this gaseous molecule is going to strike with this wall at a less force. Okay, it will strike with this wall of the container with less force, and if it will strike with the less force, this implies that pressure is also low. Since less force it is striking with, the pressure is low. It means that the real pressure is now decreased. So what have we found is that the real pressure P real is less than the ideal pressure. Since here the intermolecular force of attraction is 0, here there is the net force is if we consider 0. But here what happens, due to intermolecular force of attraction, an attraction force is created, and due to that pressure is decreased. That's why pressure of real gas is less than pressure of ideal gas. So dear students, now to get ideal pressure, since this ideal pressure is weak, we need to add some pressure term to this real gas. Okay, so this is Vanderwall pressure correction equation, where P dash is pressure correction term. Okay, now let's write this over there. So this was P ideal is equals to P real plus P dash. Okay, where P dash is pressure correction term. Pressure correction term. So now let's find this pressure correction term. Pressure correction term or P dash. Dear students, this pressure correction term or P dash depends on two factors. Okay, first one is number of molecules per unit volume of the container. Number of molecules per unit volume of container. Why? Let me draw this. Here real gases are present. Okay. So if we take a small cube, suppose this is the unit volume, and we said that pressure correction term or P dash depends upon the number of molecules per unit volume. So suppose in this container, let this is unit volume, and you see if in this unit volume, if the number of molecules are increased, then what will happen? Attraction force will again increase, and it indicates that again pressure will decrease. That means P dash is depending upon the number of molecules per unit volume, because if number of molecules are getting increased, that means attraction force, we are getting an inward attraction force. As a result, P dash is changing. So this is the first factor where P dash depend. And you see what is this? If we write this as N by V, where N is number of molecules per unit volume. Okay. Now the second factor on which P dash depends is number of molecules striking the wall. Number of molecules striking the wall. Because if number of molecules striking the wall is getting increased, that means again attraction force will increase, because more the number of molecules getting striking here, again they will be get inward attraction force in all direction. So overall attraction force will increase and again P dash will change. So the number of molecules striking the wall also depends on pressure correction term, and you know this is directly proportional to N by V, that is number of moles per unit volume. Why? Because if number of molecules per unit volume increases, then obviously the number of molecules striking the wall also increase. So that's why number of molecules striking the wall is directly proportional to N by V. Now you see both these are what? Pressure correction term or P dash. So first of all, P dash is equal to, or you can say right, P dash is directly proportional to N by V for this, and again for this P dash is directly proportional to N by V into N by V. So what happens? P dash is directly proportional to N square by V square. Okay, P dash is directly proportional to N square by V square, and if we write it, it will be like P dash equals to A N square by V square. So we get the the pressure correction term now, where the pressure correction term P dash is A N square by V square, where this A is again Vanderwall constant, and it depends on intermolecular force of attraction. Okay, so now in this P dash we can substitute this thing. So if we substitute the final pressure correction equation, the final pressure correction equation will be simply substitute this P dash with A N square by V square. A N square by V square. Okay. So finally, the two correction term that from Vanderwall proposed, that is, one is volume correction equation that we found as Vi equals to Vr minus Nv, and the pressure correction equation that is V ideal equals to P real A N square by V square, where this Nv is volume correction term according to Vanderwall, and this A N square by V square is pressure correction term according to Vanderwall. Okay. So now let's write the ideal gas equation again. Now the ideal gas says Vi is equal to nRT. But as we told, no gas is ideal in nature, and since the gases are real gases, so we can substitute those things according to Vanderwall theory, where in case of Pi we will substitute P ideal is P real plus A N square by V square, that is P real or PR plus A N square by V square, and in case of Vi we can write Vr minus Nv. Vr minus Nv, and this equals to nRT. Okay, so this is the ideal gas equation, and this is the real gas equation. This is the real gas equation according to Vanderwall. Okay, so we found ideal gas equation and we also found real gas equation that was proposed by Vanderwall.